Hi, everybody. It's a great pleasure to address you virtually. I think hopefully you'll find this talk. I recognize when I give these talks that people are coming to them with different levels. Um, so I try to, this will be a lot of nice pictures. And I will try to give a little more physical insight for some of you who are a little more scientifically inclined, but I'll also try to keep it simple enough that you can get the gist. And remember, there's no homework or tests associated with this, so hopefully just sit back and relax. So I do want to talk today about star birth, star formation. So a star is born, we're talking about actual stars, the ones in the sky. And it's been a subject of human curiosity probably since there were humans as to how things are made. Why are the stars up there? What people didn't know what they were either for a very long time. And so today, hopefully at the end of the talk, you will understand how stars are actually made. And of course, the story I'll tell you applies very much to our own sun. So this picture is a picture of the Milky Way at night. You can see the band of light across the sky. That is literally billions of stars creating this light here. But you can also see something else about the Milky Way. Of course, this picture is a time exposure. Your eye doesn't see it nearly this well. But when you do get a good picture of the Milky Way, you can see that there's this funny dark stuff that's actually obscuring our view of the main Milky Way. So the space between the stars isn't actually completely empty. There are very thin clouds, and by thin I mean much better than a laboratory vacuum. They're extremely thin, but they're also seeded with what we call dust, which comes from dying stars, and stars puff this dust out near the end of their life, and it ends up in interstellar space, and sometimes collects into these clouds. And those are where stars are formed. So here are some more close-ups. This one's some dark dust clouds seen against a bright background nebula, so you can see them a lot better. More often, you'll just notice sort of an absence of stars, and that's because this dust is blocking your view, basically. So what is the dust? It's essentially particles of silicon and magnesium and carbon with some oxygen attached that come out of these dying stars. And the particles are really tiny. They're essentially like cigarette smoke. And the density of them is extremely low. So as I said, much better than a laboratory vacuum. But the reason they look dark like this is that they extend for light years. So even if you have extremely thin stuff, if you've got a light year worth of it, eventually you can't see through it. And that's these dark clouds. And they're associated with hydrogen gas that is actually 100 times more hydrogen gas than there is dust here. And that's where you can start to make stars. So this is a nice Hubble Space Telescope picture of one of these sites of star formation. We call them molecular clouds because the gas gets to be dense enough in the inside of this that it's no longer just atomic hydrogen, atomic carbon, and so on, but it actually starts forming molecules like hydrogen, molecular hydrogen, and carbon monoxide is a nice molecule that gets formed in there. So again, the scale on this picture is maybe 10, 20 light years across this thing. So these are huge. And the amount of mass that's contained, mostly in gas, but some in dust in here, is thousands of times the mass of our sun. So if you could take all this gas and dust and turn it into stars, you'd get thousands of stars out of it. The process actually turns out to be pretty inefficient, so you only get maybe a few percent of the actual mass there that turns into stars. Here's another couple pictures of these molecular clouds. We find them particularly in the spiral arms of our galaxy because the spiral arms tend to compress the gas somewhat. And within these clouds, you can see there's a lot of structure. Within them, there are places, they're called molecular cloud cores usually, where the density of the gas and dust gets high enough that gravity can begin to actually start to collapse that core. And that's the beginnings of the star formation process. You can see the structure of this cloud is really quite complex. This cloud in particular is actually being eroded away by some bright stars that have formed out of it, and they're starting to clear it away. And so that's why it looks like there's a lot of gas sort of boiling off the surfaces of this. And this is a picture in the optical taken by the Hubble Space Telescope. Over here, we see a picture in the infrared. Infrared is better at looking through this dust. So what you can't see through in the optical, you can kind of can see through in the infrared. And if you go out to radio wavelengths using radio telescopes, you can actually see quite through it. And so we use a variety of techniques to peer inside these molecular clouds to see what's going on. I'll bring your attention to this funny thing at the top here. What's actually going on up here is there's a dense core. There's actually a star forming inside of it already, visible. You can't quite see it in this picture.
Sorry to interrupt, Gibor, but we're only seeing the first slide. So maybe,
Really?
I don't know why, but let me just.
That's weird.
Yeah. Maybe.
So I'm changing the slides, but you're not seeing that, huh?
Yeah. So maybe just.
Let me try stop share.
And then share again. Yeah. Okay. Go for it.
Huh. Okay.
I had you on spotlight.
So now I'm going to try to share again.
Yep.
Yeah, it's terrible. These pictures are great.
They are. The first one is just gorgeous. I've really been getting lost in looking at it. So we'll want to see the next one.
All right. So now do you see my whole PowerPoint?
Yeah, I see your whole PowerPoint.
Now let me hit play.
Okay.
Now you just see the slide?
That's right. But go for it.
And now I changed it. Did it change?
No. So
no. Okay. Well,
I
said PDF might be better, and maybe I was right about that. Let's go ahead and I'll fix my keynote slide a little bit here.
Fine. Everybody can kind of do a little stretch. Maybe you've been sitting too long and think
well,
about.
I can. Is this filling your screen? The keynotes.
We're not seeing your screen. If you want to try sharing it again, and I can take a second to tell people how to ask questions when the time is right. The Q&A feature is you can submit questions as we go, which people have already found. I can see it.
You can see it, and
yeah, and it's okay if we see the the ones on the side.
Yeah, right.
But we see it.
That's funny that play doesn't work, huh? All right, so that was the slide you were looking at. This was the slide I was trying to show when I was talking about the dark clouds seen against the bright nebula behind them. So these are the clouds here. You can also see them, they just block light. So this dark space here is not an absence of stars, it's a dark cloud in front of stars. And then I went to this slide, which is a nice Hubble picture of a molecular cloud. So you can see the gas looks like it's sort of boiling off the surface. Once stars form, they start destroying their birth sites. So this is a cloud that's making stars right now, but it's also being destroyed by hot stars that it made before. And then this is where I was when you stopped me. So here's another one of these clouds with a lot of structure. I talked about that. And this is the infrared picture of it, where you can see into it a lot better than you can in the optical or visible light. And I was about to describe this little thing up here. I'm going to make it bigger for me, because I guess it fills your screen, but not mine. Okay. Up here at the top is where I said there was a star forming inside this core here. And I will describe later, these two funny things coming off the side here are actually jets of very high velocity jets of material which come off of newly forming stars. And over on this side, you can actually see the shock wave where this material comes out and hits the the interstellar medium. So that's what this funny looking head is about. But here's another jet coming off of a star that's buried in here. Here's a core that hasn't yet formed a star making a jet. And this is the revolution that's happened over my career as an astronomer. We had no pictures like this at the beginning of my career, and now we have tremendously detailed pictures of the star forming process, which is why we're pretty confident at this point that we really understand how stars are formed. So once the molecular cloud core forms and starts making stars, the very hot stars start destroying the cloud. And so here, for example, is revealed a cluster of stars that have formed inside the cloud, and now the cloud is basically clearing away its birth cloud. And that happens fairly quickly within, well, I'm an astronomer, so for me, 10 or 20 million years is pretty quickly, because the universe is 13 billion, 14 billion years old. So this is beautiful. It reveals a cluster of bright stars. There's actually a lot of fainter stars here. There are actually several thousand stars that have formed here. You can only see the bright ones in this picture. And here you can see a cloud being eroded away by the light coming from here. Okay, now I'm going to sort of take you on a tour of a constellation that's up late at night now, and it's a winter constellation, the constellation of Orion, which is in fact one of the major nearby star-forming regions in our galaxy. So here's the constellation of Orion in visible light. You may recognize the outer rectangle here, the 3 stars of the belt, and then here's his sword. Obviously, your eyes don't see anything like this amount of detail. Again, it's a time exposure, but probably many of you recognize this constellation. And in this picture, you can kind of see that there's a red glow here, and a bright non-star glow here. This is the Orion Nebula that's in his sword. If you look at the same part of the sky in the infrared, it looks quite different. So what happens here is all that dust I was talking about before is being heated by the stars that are forming and glowing in the infrared. And so now you can see what looked like a nice star field with the constellation in it is really a huge complex of dust clouds. And this is the Orion Nebula here. Can't really see all the stars so well. There's one. And then there are rings like this. So this is a star formed here and starts blowing away the dust around it. The sky looks very different at different wavelengths, and astronomers take advantage of that to learn a lot more about what's going on in the sky than you could tell if you were just looking with your eye. So we're now gonna hop on our starship and zoom in to this star forming region and see what's going on there. So again, here's the constellation. Now let's zoom in on this Orion Nebula that's in his sword. So if you look in a telescope, you see this tremendous nebula here and an associated one here. What you're really looking at here is like the glowing tip of a cigar. So there's actually a molecular cloud that goes into the screen here, and we're just looking at the part that's sort of pointed at us. But that is a part where very hot new stars are forming, and it's lighting up this molecular cloud and also eroding it and destroying it. So there are thousands. We know that there are thousands of new stars here being born right now and born in the last million years or so. And this is probably a typical region where how stars are made. And we think our sun probably formed in a region like this originally. Okay, let's zoom in some more. So we'll zoom into the core of this nebula here. And now we see 4 really bright high mass stars, and they're the ones that are basically causing most of this light up. This is called the trapezium because they're kind of in a trapezoid configuration here. Let's zoom in some more. So here they are, the 4 stars of the trapezium. You can see the nebula being lit behind it. Remember, that's the surface of this molecular cloud as it's being eroded by the stars. And if you look carefully, you can see some interesting objects. Here's one here. Here's one here. look like little windsocks. And the windsocks are pointing away from this star. So these actually are places where new stars are forming, but the radiation and there's actually a wind of hydrogen blowing off of this star at several thousand kilometers per second as well. It's actually eroding these little cores where new stars are being made. So when you form stars in one of these giant molecular clouds where there are very high mass bright stars, it actually affects the formation of the stars around them. So zooming in even more, now you can see a couple of these windsock things better. Here's the main guy. This star is several tens of solar masses, and it's producing most of the energy in this region. And all of these things here are newly forming stars around this. So remember, there were thousands in this molecular cloud, and the blast from the luminous star is eating away at the other ones. And so we can zoom in on one of these, and now you see a planetary system in formation, basically. So this little object here, this is like our solar system. It's actually 2 or 3 times bigger than our solar system. If you imagine the sun and all the planets going around it, it would be a little part of this. And this windsock thing is actually the shock wave caused by the wind from the big star, which notices there's an obstacle here and forms a shock wave around it, and glows on the front end of it. But that's a real newly forming star with a disk of gas and dust around it. Here is one that you're looking down on. So now you can see the star in the middle of it and the disk of gas and dust around it. This is how our solar system was formed. Our solar system is in the plane of a disk, and that's why, because this is what happens when you make stars, and I'll explain why that is in a bit. And so here are a bunch, rogues gallery of these little windsocks. They're called Proplyds, or protoplanetary disks, in the Orion region. So again, beautiful, nice examples, various kinds. Here's a nice one. So this disk is being seen almost edge on. Here's the shock wave out in front of it. But you can see that there's a star buried in the middle there, and it's causing this glow here. And that's the one we looked at before. And as I said, the scale on these things, I might use the term AU a few times. AU is just the distance from the Earth to the sun. But the thing you need to know is our solar system, the planetary part of it, is sort of 30 or 40 AU. And this bar here is 250 AU. So this is already quite a bit bigger than our solar system. Okay, and now I want to spend a little bit of time explaining why you get a disk. And these disks are very ubiquitous in astronomy, and they're all for the same reason. So for example, you may know that our whole galaxy, the Milky Way, is a disk. The reason that it's a band in the sky is that it's a disk. The reason that we have the constellations of the zodiac is that the planets were formed in a disk. So disks are very, very common. And why do they happen? It's really fairly simple. You may or may not know the term angular momentum, but what you do know for sure is that when a skater spins and holds her arms out, if she pulls her arms in, she spins faster. You've all watched the Olympics. That is because of conservation of angular momentum. So angular momentum is, maybe you know what just regular momentum is. So a truck has a large mass, and if it moves at a high velocity, it's got a lot of momentum. And if you have a toy truck moving slowly, it has rather little momentum. So for angular momentum, it also depends on the mass of the object that's going. But if it's going around in a circle, you also probably know that if you spin a ball around in a circle like this and let go, the ball just flies off. And so you have to hold it. You feel a force that's trying to hold it in. And the ball has a certain amount of momentum as it goes around in this circle. And if I tighten the string, the ball goes faster. So you can imagine it has more angular momentum. And it's actually, the angular momentum is just the product of the speed that it goes around and how far away it's going around from the central core. So if the angular momentum is conserved, if I pull in the distance, then the speed has to go up to keep this product constant. And that's basically most of what there is to it. The other part, as far as disks are concerned, is suppose now I have that molecular cloud I was talking about, which is going to collapse to make a star, has a little bit of spin. And they all do. The reason is the clouds just sort of form out of turbulent motions in the galaxy. It'd be almost impossible to form a cloud that wasn't spinning in some direction. They don't spin very fast. The rotation of one of these clouds might take 10 million years. But now it's the conservation of angular momentum that comes into play. So gravity is going to start pulling this cloud in towards the center, but it has a spin axis. Here's the spin axis here. If I drop down the spin axis in any direction, I'm not changing how far away I am from it, so I don't have to spin any faster. But if I try to come in this way, I am changing my distance between me and the spin axis, and so I need to go faster. So basically, stuff can drop parallel to the rotation axis without much trouble, but it has a lot of trouble coming in from the sides because it has to go faster and faster. And of course, at some point, it'll be going so fast, it reaches orbital velocity, and then it has no reason to go any further. It's in orbit around the central mass. And so it'll stop there. So depending on where I started over here, I will stop in orbit at some distance from the rotation axis. But gravity is happy to pancake me. You know, if I'm here, I'm going to drop this way, and if I'm here, I'm going to drop that way. And that's why you get disks in astronomy and astrophysics. And I think I'll stop here because this is such an important point. I want to see if there are any questions about that.
So thanks. There are a couple questions, whether or not related directly to this, but does dark matter play a role in star formation?
Absolutely not. So those dark clouds are made of normal matter, the dust I was talking about. Dark matter itself is extremely diffuse on these kind of scales and really plays no role. Okay,
and John Lightfoot asks, and you'll have to pardon my pronunciation, Proplyds, those such as those in Orion, have planets? If so, are we able to detect their presence?
They almost certainly do have planets. Orion's a little far away for us to see them easily, but we have seen disks closer to us that I will show you later that definitely have planets in them. Plus, the Kepler mission that I was part of established that almost all stars have planets around them, and so the likelihood that they wouldn't have planets isn't that high.
No other additional questions unless people want, let me see, Liza is keeping an eye on questions in the audience as well at the town hall. Specific to this angular momentum problem, are there any questions in the Q&A? It looks like we got another one. Why can't material fall inward if there's gravity?
So it does try to fall inward, but remember there's this conservation of angular momentum that it also has to obey. So if it falls inward in this direction, the distance from the rotation axis hasn't changed. So remember in this picture, if the skater doesn't pull her arms in, she doesn't go any faster. If she does pull her arms in, she goes faster. So if this parcel of gas drops this way, it doesn't have to go any faster. But if it tries to go this way, that's like pulling the arms in, it has to go faster. And in fact, it'll go faster and faster until it's in orbit, basically. And then that will make a disk, because different particles in here will have different amounts of angular momentum, so they'll end up at different orbital distances from here. But it's fine if it pancakes parallel to the rotation axis. That doesn't change the angular momentum, and so that's allowed. So that's why you get a flat structure, which is in orbital equilibrium at some point. It's stable. And in order to make a star, you actually have to get rid of angular momentum somehow, which in ways I'll talk about next, basically.
Can you explain real quickly about what is quote unquote in orbit.
Oh, in orbit, it's just like satellites in orbit around the Earth. So turns out if you go around a central mass with the appropriate speed, you don't fall into that mass. Basically, you're always falling, but your path is also always curving. So essentially, you fall round and round. The Earth is in orbit around the sun. Same process again. The Earth has the right speed at this distance from the sun to stay at this distance from the sun. It's falling towards the sun all the time, but it also has a sideways velocity, and that gives its path a curved path that is basically just our orbit. And that's a stable situation, lucky for us, right? So the Earth is going to stay in orbit essentially forever. And this stuff here would stay in orbit essentially forever, except there are other processes at work that I'll get to that allow some of it to fall in all the way to the center and make a star.
All right, no more questions, Gibor, go for it.
All right, so so now I'm going to talk a little bit about some of those processes, but I also need to bring in one other fact here. Magnetic fields control charged particles, and the gas that I'm going to be talking about is charged. It's a plasma, so the electrons and protons are stripped away from each other. Once that happens, gas has to sort of follow magnetic fields. So you've all seen the iron filings follow a magnetic field around a magnet. On the sun, it's plasma, and there's a magnetic field on the sun, a lot of different ones. And so the solar plasma follows the magnetic fields as well here. So magnetic fields can control gas motion. That's really the only point I want to make. And so now what happens as this collapse occurs, several things go on. So remember, it was easy to fall parallel to the spin axis, which is this blue line. So stuff fell in first from there. That kind of makes a cavity in the original cloud. The stuff that is easy to fall in falls in first. And of course, it falls in from both directions. Remember, there's the only up or down here is the central mass is down and everything else is up. And the stuff coming in from the side has the angular momentum problem. So it has a harder time falling in, and then it falls into some distance on this disk that is forming. Meanwhile, it drags magnetic field with it, and the magnetic field concentrates. And then it turns out the star starts producing magnetic fields on its own, and they start controlling the gas motion. Let's see, did I include? I didn't include a specific diagram. Basically, the magnetic field starts trying to wrap the gas. The gas is now being forced to move at the wrong velocity, and it starts to flow back out. And so you get, because of the magnetic field on the disk and on the star, trying to control the gas motion, it starts flinging it out. It's sort of like attaching the gas to a string and swinging it. And then the gas is like beads that slide up the string, basically. So you get two kinds of outflow again. One is sort of this broad outflow that comes off the disk itself. And then the star, of course, is much, much smaller, and the field is stronger, and it wraps much tighter. And so you get a strong, much faster jet right out along the rotation axis. So essentially the stellar field is wrapped around the rotation axis, and the gas gets forced out on it. And this is an actual picture of a star in formation. It's an edge-on disk. So the disk is actually here and blocking the light. This cavity here is what makes these two bowl-shaped things. And this fast stellar jet is this green straight thing in the middle. So we see that. It's not like we have a theory about this. In fact, the theory came after the observations, really. We said, oh, well, you know, what's going on there? That's what's going on there. And so here is another Hubble picture of a beautiful star in formation. Star is buried again in the cloud here. And here are those two jets that come out the rotation axis caused by the star itself. And then there's another star forming here, and its disk wind, which is a broader thing, is producing this sort of big cavity here. and there's another one over here. And so these are the other things that happen during star formation that tend to shred the star forming molecular cloud. So again, once stars start forming, they'll form for 10 or 20 million years, and by that time the cloud will be so shredded that star formation will stop again. All right, that's one way that this process actually gets rid of angular momentum. Basically, the gas that's flowing out here carries away angular momentum with it, allowing gas that remains to drop closer to the center. The other process, and really the main process that happens is, and I'm going to give you a description that astronomers would cringe at, but it'll sound okay. It gets the conceptual idea. The other way that angular momentum is sort of transferred is it's called viscous accretion, but basically the orbits here, the closer you are to the central object, the faster the orbit is, right? So Mercury orbits faster than the Earth does. Same with all the disk material. So inward, faster moving material rubs, if you like, on material that's further out that's moving a little bit slower, and they rub together, and basically angular momentum is transferred from the inside to the outside. And if the inner material loses a little angular momentum, it can move a little closer to the central star. And so this is a way that essentially angular momentum is transferred from the inside to the outside of the disk. Material is thrown off of the outside where it has gained all this angular momentum, and the material on the inside moves closer and closer to the star, and eventually ends up on the star, some of it, if it doesn't get blown out in one of those winds we were just talking about. So that's the main actually mechanism by which the star manages to build itself, even though it had this huge angular momentum problem. So the disk is actually there to mitigate the angular momentum problem. Happens to be a great place to make planets too. So if you like, planets are sort of a result of nature trying to make a star and needing a disk to make it. And as it happens, you get planets in that disk. You can think of it that way. The structure of the disk is like this. And I'm only telling you this so you can understand the next pictures. Right near the star, there's some mechanism of accretion that I'll also talk about in a bit. It's too hot here for the dust to exist anymore. The star evaporates it basically. So there's some gap between the star and the inner part of the disk. The inner part sees the star and gets hot, so it puffs up a little bit. But then as I move out here, I'm getting further and further away from the star, and the disk is only being confined really by the stellar gravity, and so it's free to sort of puff up as you move out. It feels weaker and weaker gravity, and it just kind of gets thicker and thicker in size, not in mass here. And meanwhile, the dust stuff starts aggregating and dropping to the midplane of the disk. And that's sort of the beginning of the planet formation process. So, and then this part here, because this disk is flared like this, it can still see the star. So there's a hot outer layer, and then this is shielded from the star in here, and that's cold. And dust begins to coagulate and settle in there. Now, in case you didn't believe that, here's an actual picture of a star-forming disk. It's about 400 light years away from us. And only in the last 20 years or so have we gotten good enough with our techniques to actually make an image that can see something with this much detail that far away. I'm not going to talk about the technique, but this picture was taken from an array of telescopes, including these 4 large telescopes. This is a European observatory, and some extra ones, and a great technique called interferometry gives you this kind of resolution. So now we can really take pictures. And so here you can see the flared disk, basically. This is the disk getting larger and larger on the outside here. The inner part is shielded. So that's the shielded part in there. And this is the sort of the outer surface of the flared disk. And here's a whole bunch of pictures like that. Some of them you can see the jet still coming out. Here's the disk in the middle, the flare there. Here, this one's more flared. You're actually lighting up the cavity of the incoming cloud there. All kinds of good. This is called the hamburger disk. But my only point really in showing you these is that, yeah, we really actually have really good information on star formation these days because of recent advances in observational techniques. And this is another kind of telescope. It's not quite a radio telescope. It's definitely not an optical telescope. It works at wavelengths that are kind of a little like microwaves, like in a microwave oven. It's called millimeter waves. Again, there's an array of telescopes here, and a clever technique called interferometry allows us to see things in much more detail. And so all of these are pictures now in this sub-millimeter wavelength, which really shows the warm dust nicely of disks around newly forming stars within a few hundred light years of us. Some of the disks show some real structure, like these rings and things. And right now, the belief is that those things are usually caused by planets having formed in the disk. So this isn't a talk on planet formation, but you can see at this point that now we're at the point where we really have actual views of planetary systems in formation with these things. Here's a detailed one. Lots of different rings in this disk. And this star is only a couple million years old. We know that. Okay, and then let me say a little bit about the final process of accretion onto the star, just partly because this was one of my areas of research earlier at Berkeley. So I study stellar magnetic activity. We were able to show that these extremely young stars have extremely strong magnetic fields. So strong, actually, that they interrupt the disk at some distance away. And remember, we said the gas is forced to follow the magnetic field lines. So actually, the final plunge onto the star happens along these field lines, and the stuff hits the star in particular spots on the star and hits it hard because it doesn't come in by orbiting in. It falls in forced to go at the wrong velocities by these magnetic fields. So it slams into the star and makes the star surface much hotter where it hits. And we can see evidence of that as well. So the final plunge is called magnetospheric accretion. All right. So at this point, I'm going to stop again briefly and see what questions people have, because at this point we've made the star, and we've also essentially had to make a disk of gas and dust around it, and that is the site for star formation. I'm sorry, that is the site for planet formation. So as we did this research, before the Kepler mission and before we even discovered any exoplanets, it was becoming clearer and clearer that planets are probably not a rare phenomenon. In fact, they're probably sort of a natural consequence of star formation. So now that you've seen the star formation process, you understand that statement. And then it was essentially a confirmation of that idea as we started finding exoplanets in great numbers. So that's actually the main part of what I wanted to say. I'll go in a little more detail of planet formation if we have time, but I do want to stop here and take questions on star formation.
Thanks, Gibor. I have a couple questions in the Q&A, and I think Liza's polling the group at the town hall to see if they also have questions that she'll type in. Is gravity constant for all star formation?
Well, let's see. I mean, gravity, of course, is just a force between masses, so that's constant. But what isn't constant is the amount of mass that's there in each different star-forming core, the amount of angular momentum that's present, the density of the material. The denser it is, the more mass you'll have concentrated into a smaller volume. So the gravity near that would be stronger than if you spread the mass out. So in that sense, no, each system is different, but the effect of gravity and the physical force of gravity is always the same. What matters is, how much mass I have, how concentrated it is, and how fast it's spinning basically around the axis. And those things can be quite different. I mean, we do see that stars of different masses are formed with different frequency. So it turns out the sun is not an average star. Actually, the sun is 2 or 3 times more massive than the average star. Everybody always says, "Oh, the sun's an average star." Well, not actually. So about 3/4 of the stars in our galaxy are, half a solar mass or less. So that's actually the typical star that results from this process. It's what we call a low mass star, or red dwarf. And the sun is a little bit unusual. So a few percent of stars have the mass of our sun. And then we do get higher mass stars as well. And they're trickier and trickier to form. And so there are fewer and fewer of them. So once you get up to, say, 10 solar masses, it's a fraction of a percent of stars that form that are that massive. Yeah, there's a number of other properties of stars that vary a great deal with their mass. But in terms of formation, we do know essentially how often nature likes to make each kind of star or each massive star. And the dominant star is sort of a third to a half the mass of our sun.
Okay, great. We have a number of questions in the Q&A, but I want to open up just to Liza. She has a couple questions from the group in Town Hall. So let me unmute you, Liza, I hope. Let me make sure I've got the right one unmuted. Or you unmute yourself there. There you go. Go for it.
Can you hear me okay?
Yep.
Great. We're going to start with our question from Lee.
Okay. You seem to be at times.
I can't hear that.
At times it sounded to me like you were talking about star formation and planet formation sort of interchangeably, as though they had some of the same processes. But then it seemed like you're saying planet formation is always a result of star formation and happens in the rings around the star. That's my question.
Do people still see my screen?
Yes.
My slide?
Yes.
Okay, so here is sort of a cross section of one of those disks, and the point is that the first point is that you almost always get a disk when you're making a star, and then in that disk, what happens is the outer surface can be hot, but the inner part is shielded from the starlight and gets quite cold, and the dust starts to coagulate, and as it coagulates, it tends to sink to the middle. Remember, gravity in this picture if you're here, you'll drop this way, but if you're here, you'll drop that way. And dropping that way is hard because of the angular momentum issue. So basically, the disk will start accumulating denser, more coagulated material in the midplane, and that stuff will eventually end up or can end up as planets. So it's kind of a result of the star formation. The star formation process gives you this disk, and once you have the disk, it's reasonably likely that you may make planets in the middle of it. Does that answer the question?
Yes, thank you. We have another question.
Hi, I was wondering, where is the ALMA array located?
Yes. So these discs, or dishes, I guess is the right word. These dishes are sitting in the Atacama Desert in Chile, and the elevation of this plateau here is about 16,000 feet. I actually had the chance to go visit that observatory last year. The base operations occur in a building that's down at about 9,000 feet. This 16,000 feet is not a pleasant altitude to work at. And so actually what happened was we went to the base station, we got a talk, and then they did a medical check on each of us. They took our heart rate, our blood pressure, and blood oxygen. And some of us were told we may not go up to the observatory, and some of us were told we may, based on our health. And I was one of those who was not allowed to go up to the observatory because my heart rate was too high. We'd been at altitude for a couple of days, and so there are several observatories. This other one let's see, where's my picture here? This is also in the Atacama Desert in Chile. You know, why Chile? Well, these are both European facilities. Well, actually, this one's international. They don't have great weather in Europe. And if you want to do millimeter astronomy, you really don't want water vapor above you. So you really want to put, they want to put these at as high an altitude as possible to get above most of the Earth's water vapor, which blocks these wavelengths of light. So it's really high up there, and I didn't actually get to go because it was a dangerous altitude for, especially for older people. It's you don't go there.
Fascinating. I think this question was answered in the disk question. Does a disk remain once the star is formed? I think you might have answered that in a way.
Well, actually, no, I didn't. I didn't answer that. So this is the picture of star formation, probably a million years or so into the process. There's still a pretty good jet here. There's still a lot of disk. And then what happens to the disk? We can see them going away. So with observations like this, you know, you can see the disk disappear over time. And of course, we don't watch an individual disk disappear over time, because that's a sort of a 10 million year process also. But what we do see is we see disks in different stages of being disappeared for stars that are of different ages. So what happens to the disk? Well, several things. One is that the star, remember, has these very strong magnetic fields, and it develops a strong wind blowing off the star, and that starts eroding the disk. The magnetic activity on the star also produces a lot of ultraviolet and X-ray light, and that starts eroding the disk as well. And then you've got this process where the disk is settling down, and the pictures that I was talking about, these pictures here, are only sensitive to extremely small dust particles. So once you start building that into sand-like particles, for example, or rocks, you're not going to see it anymore. So the disk disappears in that sense. It hasn't, all that mass hasn't gone. Most of the gas has been blown away by the star, essentially. But the rocky stuff and some icy stuff, if you go further out, is still there. But it doesn't show up as a disk like this. So essentially the disk starts converting to a planetary system, if you like. What's left of it.
Right.
Most of the mass of the disk is actually blown away as gas during the first 10 million years or so.
Are the sunspots created by magneto accretion?
Yeah. No, they're not. Okay, so this picture shows two things. It shows dark spots and also bright spots. The bright spots are created by magnetospheric accretion. That's just the shock wave as stuff falls from the disk through the magnetic field lines onto the star. Where it hits, you get a bright spot. These dark spots are actually caused by the internal magnetic field of the star coming out through the surface of the star. Basically, the whole star is what we call convective, or it's transferring its energy out to the surface through essentially a boiling motion. But when the field is very strong, remember, it controls the plasma, and it kind of stops that boiling, and then that part of the star cools off some, and that's why you get these dark spots. So the dark spots are the star's magnetic field, and the bright spots are disk material falling through the star's magnetic field and hitting the surface. So we do see both kinds of spots on these very young stars, and then once the accretion stops, you only end up getting mostly dark spots.
And why are astronomical magnetic phenomena so hard to understand?
Yeah, well,
rhetorical question. But
right. Yeah, if you looked at the equations, you'd see why they were so hard to understand. Basically, the magnetic field and the gas interact with each other in very tricky ways. This is one of the reasons we haven't invented fusion power on the Earth yet. It's the same kind of problem. We want to confine this very hot plasma with magnetic fields, but the magnetic fields in the plasma are very squirrely. They love to exchange modes and energy and so on with each other. And we've been unable to confine hot plasmas sufficiently to get fusion to happen in Earth reactors. The stars just do that confinement trick by just having a ton of material, weighing down on their core. So, whatever it tries to do is still getting crushed by all the weight of the star. So there you can get fusion there. But on the outside here, it's pretty tricky what goes on.
When in this process and it might have been in context of when in this process does the star ignite?
Yeah, that's a really great question, actually, and I didn't really talk about the star igniting so much. So as you are accreting the star, as the star is being formed, once material arrives on the stellar surface, gravity still wants to pull it in to the middle of the star. The star is resisting that with the internal pressure that it has, and what happens first is that as material moves towards the center of the star, it's dissipating gravitational potential energy. What do I mean by that? Well, if I pick an anvil up and drop it on my foot, it hurts because by the time the anvil reaches my foot, it's picked up some momentum. So essentially, I've converted gravitational energy into energy of motion, and it hurts. In the case of the star, as the star contracts towards its final size, you're dissipating gravitational potential energy. Turns out that source of energy is actually significantly greater than the fusion energy that the star will end up with. So our sun was several times brighter than it is now when it was during this contraction phase during formation. Eventually, the contraction is stopped by the fact that the internal energy and the densities are able to hold the star up against gravity. And that's when fusion energy becomes more important, because of course the star is also losing energy all the time. It's shining, right? So in order to hold it at a given size, I need to keep resupplying energy. So essentially the sun gets energy from gravitational contraction, but keeps contracting until the point where it gets enough energy from fusion to hold it at that size and stops contracting, and then its main energy source is fusion. But it used to be quite a bit brighter during this formation phase than it is now.
So there's 5 more questions and it's noon. Is there other content you want to cover before or do we just want to keep answering?
No, this is better.
It's fun, huh? Yeah. So the Earth is a remnant of the disk that formed the sun? That's a question.
You could think of it that way. That's right. You could think of it as a lump that got left in the disk after the disk dissipated. So are the rest of the planets.
All right. And why does the dust star having regions of spin in the first place? Start having regions of spin in the first place? Yeah.
So the initial spin that we had to get rid of, the angular momentum from, that initial spin comes from. Let me go back. Say here. So here's the molecular cloud before it's making stars. Where how did this collect up? Well, the stuff that's here used to be spread out much more thinly between the stars, and it was just kind of going here and going there, and this part ran into that part, and that part ran into that part, and there was a spiral density wave came through and compressed things. A very turbulent, chaotic, random process. So as you can imagine, the motions in here are kind of all over the place. Now, if we're going to take a little piece of it and start collapsing it, there's going to be some net spin in some direction, just because stuff's going hither and yon. So really the initial source of that spin is just turbulence in the process that formed the cloud in the first place. And I'm going to pull out a little piece and try to collapse it into a star. So I'll end up with some spin. As I said, it's not much spin. The core that's going to collapse to a star might rotate once every few million years. Doesn't even get to, of course, do that because it's going to collapse to a star. But that's the angular momentum that it has. And that gets to be much, much more of a problem. Remember, the skater pulls her arms in and makes them maybe, a quarter as long as they were when she had them stuck out. In this case, I'm going to take something that's a couple light years across and try to shrink it down to the size of a star, which is a couple light seconds across. So there's an enormous amount of shrinkage. And so what was a very tiny amount of spin when the thing was huge becomes really problematic as it starts getting to be the size of a solar system. And because the galaxy has typical amounts of turbulence, solar systems have typical sizes. These disks have typical sizes, and those sizes are a few hundred AU, a few hundred times the orbital distance of the Earth from the sun. And that's reasonable with our own solar system. So that size, the size of planetary systems, is really just set by the amount of turbulence that these clouds get when they form.
Are the disks around a sun all on the same plane with the equator of the sun?
That's another great question. Not quite, but usually fairly close is the answer. There's another process I said nothing at all about, which is we often get binary stars. So 2 stars form instead of 1, and that can tilt things. But our own sun is about 8 degrees off. The equator of the sun is about 8 degrees off of the plane of the solar system. So it's not perfectly aligned. You can get processes like the accretion that happens might not happen exactly in a plane because you got this funny process, for example. Or you can actually get the tilt of the disk can be shifted a little bit by the presence of other bodies nearby, like other stars may pass nearby and tilt things a bit. So yeah, it's not usually exactly aligned, but it's usually reasonably close.
This is Rosemary asks a more technical question. If the gas starts out ionized, the whole process must go at different rates for electrons and protons. What effect does this have on the formation, and how does the star and the dust get T equal neutralized? Maybe that's neutralized, or is that?
That sounds pretty technical.
Yeah.
Let me just say the main part of the disk is not ionized, or it's barely ionized. This cold part in here. This hot surface layer is ionized by the UV and X-ray from the star. By the time the magnetospheric accretion occurs, it's all ionized. It's plasma there. But so yeah, it's a very complicated question with a lot of different answers depending on which part I'm talking about. So I'll leave it at that. And I probably can only take about one more question.
And there's just one more question in the Q&A. Why do stars have large magnetic fields?
Okay. Yeah, I didn't put the slide in here, but basically there are 3 ingredients needed to produce magnetic field. The process of producing magnetic fields is called a magnetic dynamo. So I'm sure you're aware the Earth has a magnetic dynamo operating. The sun does, Jupiter does, actually most things in astronomy do. And what you need 3 ingredients. First of all, the thing has to be spinning. Okay, well, we solved that problem. In fact, we had to get rid of a lot of angular momentum. The next thing is it needs to have conducting material in it. But a plasma is a conducting material, fully conducting. So any star will have conducting material. Any star will be spinning. The third ingredient you need is essentially these boiling motions called convection. And newly forming stars, it turns out, are all fully convective, so not a problem there. The current sun is only convective in about the outer 30% of it. And so magnetic field is only produced in the outer 30% of our current sun. But originally, the whole star was convective, and the whole star produced magnetic field. And the faster you spin it, the more magnetic field you produce. And the young sun was spinning 4 or 5 times faster than it is now. So that's why it had a very strong field at that point. And that's typical.
Well, there is one more question, but I want to be mindful of time. I know you have another talk to get to. Maybe
I'll take one.
okay.
I'll make it fast, but then
All right.
then I'll say goodbye.
And then you'll say goodbye. Thank you so much, Gibor. It takes about 10 million years to form a star, so we can't exactly take a time lapse of this process. But do we know enough to be able to create an animated model with computer calculations?
Yeah, well, we can do that in the computer, but we also have the way we do things in astronomy, generally speaking, since hardly any of them happen on human timescales, is you look around and you try to find snapshots of the process at different points. So it's like if you want to know how humans evolve, you know, if you take a picture of a crowd, you're going to see little kids, you know, babies, adolescents, adults, old folks, they're all there. If you can identify what age they're at, you can say, oh, I can see what happens to humans over time. And so that's exactly what we do with these stars. It's especially handy when they're in clusters, because it's easier to date a cluster than it is an individual star. And then you have a bunch of stars in the cluster that are different masses. So you can say, oh, that mass looks like this at this age, and that other mass looks like that. And that's how we put it all together. But yes, we also can do computer models at this point. And then we can test them against these observations and see if they're right. Well, thank you all for listening. It's a fascinating topic. Maybe some other time you can invite me back and I'll tell you how to make planets.
We'd love that, actually. So thank you so much. Have a good rest of your day, and best to everyone.
Thank you.
We'll have a recording out for this and the slides soon.